Yeah, hello everybody. Please welcome Anna Herlihy. She's talking about wrestling Python into an LLWM intermediate representation. So please welcome Anna.
Hi everyone. Like was mentioned, my name is Anna Herlihy, and I'm going to be talking about PyLLVM, which is a compiler from a subset of Python to LLVM-IR. So this project was the result of some very specific circumstances and some very specific requirements. I'm not going to stand here and argue that this is the best little compiler you've ever seen, but I will say that it is an awesome project that was born in a true open source capacity. So if there is a moral to this talk beyond the technical content, it is that you got to be careful with your projects. You may think that they are dead and gone, but then somebody like me will find your code on the Google Code Archives and breathe new life into it. Something else I should mention is that I've been battling a pretty bad cold for the past couple of days, so I want to apologize in advance for any lack of inflection. So about me, I work for MongoDB in Stockholm, Sweden, although what I'm going to be talking about is actually some work that I did as an undergraduate. So I'm going to give you an outline first, a little bit about what you're in for. First, I'm going to talk about the motivation behind this project and the very specific requirements that we had to meet. I'm going to go through the features of PyLLVM, a little bit about how it works. Then I'm going to talk about related work, mostly Numba, which is a just-in-time compiler from Continuum Analytics that uses similar tools. I'm going to do some analysis before we can finish up here. So how did I get involved in this project? So Tupleware is a distributed analytical framework built at Brown University. It basically allows you to run algorithms on large data sets and have it be automatically deployed on a distributed cluster for you. So while there are a lot of distributed analytical frameworks out there, like Hadoop MapReduce, Spark, etc., what makes Tupleware unique is that the goal is to be both language and platform independent. So what does that mean? There are a ton of different people who want to run analysis on data, and they have a bunch of different skill sets. So some people really want to write their algorithms in Python. Other people prefer R or some other language, and we don't want to have to limit our user by their preferred language. Platform independence is the other side of things, where we don't want to limit people to a specific architecture. We want to be able to run on whatever you want your cluster to be built on. So how does Tupleware achieve both language and platform independence? Through LLVM. So LLVM is a lot of things. What we are going to talk about is LLVM-IR, which is intermediate representation. Intermediate representations are a way of representing code that is in between the source code, which in this example is Python, and the machine code. So you can see there are a bunch of different logos for different languages. The dragon is the LLVM logo, which is awesome. But what's so great about the LLVM project is that there are so many existing compilers to so many different languages. So it's pretty nice because a lot of the work is actually done for us. So what is the goal of this project? I'm not going to go into the specifics of how Tupleware works. That is an entirely different talk done by entirely different people. But what I worked on is specifically providing a comprehensive Python front end for the Tupleware project. So Tupleware itself is written in C++, and when I joined the project, which was about 2 years ago, the user had to write their UDFs, which stands for user-defined function, in C++ and had to interface entirely in C++. This is usually where I would go into why Python. Sorry, but since we are all here, I'm going to assume we are all properly indoctrinated and we all love Python. So where does this talk fit into the greater architecture? On the left, you have the workflow and the algorithm. These are the two things that the user supplies. And on the right, you have Tupleware itself. What my project does is it brings the two together. First, we need to be able to access our Tupleware operators, which we used Boost Python, which is pretty straightforward since we were already using Boost for a bunch of other stuff in Tupleware. And then PyLLVM moves the UDFs in Python into LLVM-IR. The IR can then just be directly passed into the backend where it's deployed and all the other stuff happens. So I wanted to give you an example of what a tupleware usage would look like. This is a simple linear regression algorithm. You don't have to worry about what it's doing, but it is worth it to look into what the code looks like. So since there are so many different Python features, and they're all really cool, but not maybe all so useful, we really wanted to hone in on what exactly a sample user would be likely to use. Like, what subset of Python are they most likely to actually make use of? On the other side, you have how you would interface with tupleware itself. So you first load your data, you run map, and you call execute. This is pretty much the simplest workflow possible. If you go one level down and you take a look at how the tupleware library itself is implemented, it's also pretty straightforward. The first thing we do is we try to get our LLVM-IR out of the UDF using PyLLVM. If this fails, then it's possible we have functionality in our UDF that isn't supported by the subset of Python that PyLLVM allows. And if this is the case, then we have a backup method, which basically uses the Python C API to create an executable. The backup method is there so that the user has no idea what's supported. They don't care. They just want to write their Python, and they want it to run. But if we get an error there, then we know there's a problem somewhere else. Otherwise, we can just pass the IR that we generated directly into the backend. So PyLLVM itself. This, like any good engineer, when I first pinned down the requirements that I needed to meet for this project, I searched, hoping that maybe somebody had done the work for me. What I found was PyLLVM, which is basically an unfinished proof of concept that sort of stopped being actively developed maybe 5 or 6 years ago. What PyLLVM uses to generate code is called LLVM-Py. I know it can be kind of confusing. There's only so many ways to combine Py and LLVM, but LLVM-Py is basically just a wrapper around the C++ LLVM-IR builder tools, which is what actually generates code. That's provided by the LLVM project itself. So something else that's kind of cool about this is when I first did this research about 2 years ago, I looked to see if anyone else had contributed to this project or if there was anything similar, and I pretty much couldn't find anything other than Py2LLVM. But when I wrote this talk not so long ago, I realized that there's now a bunch of different repos out there, and people have forked from the same place and taken the project in entirely different directions. So that's pretty satisfying for me to see. So like I mentioned, there's a ton of different features we could choose to support for our compiler, but since in the interest of time and feasibility, we needed to really hone in on what type of Python a sample tupleware user would be using. So since the goal of tupleware is to run machine learning algorithms on large data sets, the nature of core machine learning algorithms is that they're pretty straightforward. They're pretty simple mathematical functions, and they're very easily optimized. So we decided to focus on that the first layer of Python. We're not worrying about decorators, objects, that kind of thing. So this is an overview of the PyLLVM compiler. This is where the compiler experts in the audience might get a little bit bored because there's nothing particularly out of place here. In order to compile code, the first step you need to do is generate an AST, which stands for an abstract syntax tree. That's basically a tree representation of what the code is doing. Luckily, this is handled by the compiler package. So this step is where you would catch syntactic errors. So say, for example, you're coding and your cat walks across your keyboard. That would be a syntactic error, unless you have a particularly adept cat. But anyway, the next step is semantic analysis, which is where we actually dig into what the code is doing. This is handled by a visitor class, which is a pretty common pattern for compilers. It basically walks the tree and does something different depending on what type of node it reaches. The last step, code generation, is handled by LLVM-Py. So something very important to note about LLVM-IR and other intermediate representations is that it's in SSA, which stands for Static Single Assignment. This means that For every register, you can assign to it only once before it is frozen. If we were to design our compiler so that registers were variables, we would then have to require our users to only assign to their variables once, which is obviously not a reasonable expectation to have. So how do we get around this? We have something called symbols, and symbols are basically variables with some metadata. They keep track of where we store the content of the variable on the stack, and then some other stuff like memory, some stuff like the name, the type, etc. We keep track of our symbols with a symbol table, which is basically a stack of tuples, where every time we enter a scope, we can push onto the stack, and then when we leave, we can just pop it off when stuff goes out of scope. So now I'm going to go through the different types that we support. So LLVM-IR provides 2 numerical types and 5 derived types. I'm going to go through each one of the PyLLVM types and talk about how we managed to wrestle Python types into LLVM-IR types. So LLVM-IR is statically typed, as most intermediate representations are, and Python is not. So this is going to be a big problem pretty much for everything, since Python doesn't indicate a lot about type from the get-go. So what we did to get around this is something called a type inference node. So if you are generating like a function call or something like that, you need to know the type before you actually generate the code, which means that we need to anticipate the types of expressions before we actually evaluate them. We do this by recursively descending the abstract syntax tree until we reach a leaf. If we reach a leaf and it's a constant, then we know what type it is because we know it's either an integer or a string or something like that. If we reach a variable, then we can look it up in the symbol table. If we reach a function call, then we can either look it up in the symbol table or we can check the set of intrinsic math functions that come with the language. So numerical values, pretty straightforward. This was implemented before I started contributing. I added booleans, which are basically just integers. Next up is vectors. So there are 4-element immutable floating point vector types, which was also implemented before I started contributing. This was actually a big part of why we decided to build our project off of this one as opposed to starting from scratch, because it's very common in a lot of machine learning algorithms to use these 4-point vectors. So we got this one pretty much for free. Next up is lists. So this is a bit of a work in progress, since there are a lot of things that come up with having efficiently resizable dynamic length lists. But what we do have, as anybody who has ever coded C knows, you have a problem where if you allocate a list and you have a list of pointers and then you return it from a function, the things that your pointers are pointing to are going to immediately go out of scope. So how do we get around this issue? Oops. We get around the issue by allocating it on the heap, actually. So this is one of those problems where we sort of got deeper and deeper and deeper into it before realizing that it was actually probably not worth it to implement our own garbage collector or reference counting or anything like that. So what we ended up doing is we just have to be very careful when we pop stuff off the stack to make sure we don't have memory leaks. Next up is strings. So since strings are basically a list of characters and characters are basically integers, we get this one for free. Since the only time you actually need to know the difference between a string of ints and a list of ints and a string is with a lot of either built-in functions or with comparisons. Next up is for function calls. So this is one of the few places where we actually do 2 passes on the compiler, since we need to know what the return type of the function will be before we generate the function signature. So the way we get around this problem is by doing one descent where we figure out what the return type is, throw away all the IR that we generated, and then do a second descent, this time knowing what the type that we are returning will be. Function arguments have the same issue. Unfortunately, this one is a bit trickier because there's no easy way to do 2 passes. We also figured in the interest of keeping things simple that it wasn't worth our time to go digging into how to anticipate function argument types. But what we did do, which may or may not be a dirty hack depending on your definition of a dirty hack, is we take advantage of the default function arguments and allow the user to provide the type of their arguments. So I think this was a decision that was made because the likelihood that you're writing a machine learning algorithm and you don't know the types that you're passing into your function call is pretty low. Next up is we have a set of intrinsic functions. This is a huge benefit if you're writing mathematical functions. You don't want to have to import an entirely different library to call square root. But the problem here is that LLVM-Py is a pretty old package that is not being developed anymore. And so it doesn't provide direct access to the LLVM-IR builder tools for square root instructions, for example, and for some other built-in function calls like print. So the way we got around this is by generating in the header some function calls that actually called the LLVM instruction, but called it something that we could pop onto the symbol table, and then we can call that function, which then calls the LLVM instruction itself. So this works the same way for print as it does for square root and a bunch of other mathematical functions. The nice thing about print is that when I first started on this project, I was basically generating LLVM-IR and reading it to make sure that it was doing what I thought it was doing. And I don't know how many of you have spent a lot of time reading assembler. It's not very fun. And I could run my executables, but I had no idea what they were doing. So when I got the print function working and my mystery executable started actually printing stuff to standard out, stuff that indicated that it was actually doing what I was expecting it to do, was probably one of the better moments of my coding career. Next up, branching in loops. So LLVM-IR has pretty straightforward compare and jump instructions. There are some idiosyncrasies. You can look up nodes if you're interested. I'm not going to go in depth, but basically there are some limitations to what you can do in different branches so that we can generate reasonable IR that can be optimized. So now I'm going to talk about related work. Numba is a just-in-time specializing compiler from Continuum Analytics. The purpose of Numba is to run your Python code really, really fast. That is not the purpose of PyLLVM. What Numba does is it uses LLVM to create these really, really fast executables, but LLVM-IR is only one step along what I think a 6-step process. So while Numba uses the same tools, it actually has a very different use case. Also, because Numba is a JIT, it means that it's lazy. So it doesn't actually compile stuff into LLVM-IR unless you run it, which is the opposite of PyLLVM, because you can't actually run anything with PyLLVM. It's just a compiler. So the bottom line is that what PyLLVM is basically a proof of concept. What Numba is something that I would recommend you use in production. Definitely wouldn't recommend you use PyLLVM in production. Another huge benefit of PyLLVM is that it's built in-house, which means that we were able to specialize it for our particular needs. And also I needed something to work on, and I have always wanted to write a compiler to LLVM-IR. So because the difference between Numba and PyLLVM are sort of big enough that it's not easy to compare the two from a benchmarking standpoint. So instead of just focusing on that, we wanted to focus on a couple different metrics for success. We wanted to make sure that we weren't limiting our users more with a Python front end than they were limited with a C++, because that would definitely be a failure. We wanted to make sure that the code, the IR that we generated, was actually optimizable and wasn't, for some reason, much, much slower than if we had used Clang or some other tool. So we picked a couple sample algorithms. For usability, you can see the same algorithm on the Python and the C++ side. They're not shockingly different, but that's the point. So the nature of these machine learning algorithms is that you don't need a lot of fancy functionality, but it does free you from worrying about pointers, structs, etc. So for benchmarking, like I mentioned, comparing with Numba, we did compare the two, but I'm not going to go into detail because it'd be very complicated and I'd be making a lot of side notes. But what we did focus on, something else to note about the compilation time is that that happens only once. And then you analyze your workflow, you deploy to your distributed data set, and the time it takes to actually compile the UDF is so minimal compared to the time it takes to run your algorithm that it's not a huge deal. We don't want to be an order of magnitude slower, but we don't actually care if we're slightly slower. Something we did want to compare is between Clang and PyLLVM. So we had the same algorithms that are written in C++ and in Python, and we wanted to run them to make sure that we hadn't accidentally created this unoptimizable nightmare IR that just ran much, much slower than what Clang was producing. So these are the results. The x-axes are the different algorithms. The y-axis is the time. The blue is PyLLVM, and the red is Clang. So as you can see, across the board, we are slightly slower with PyLLVM compared to Clang, which I have to say is not so bad, given that Clang is a huge project with a ton of resources. So if you zoom in a bit at these results, you can see that our worst algorithm is k-means. And why is that? Well, k-means requires a square root call. So it seems like our indirection is actually costing us and is not being optimized away. The idea of generating this IR and then having it be later compiled down to different machine codes allows really powerful optimization passes to happen on the second part of the compilation. But unfortunately, for whatever reason, these things are not getting optimized away. Sorry. The trouble with that is that there's really not much we can do about the fact that LLVM-Py doesn't allow us to call those functions directly. We can either upgrade to a newer version of a separate package called LLVM Lite, which we should definitely do in the future, but didn't really exist at the time that this was being written. Or we could reinvent the wheel. That doesn't sound very fun. Or we could try to come up with a different solution. So overall, we decided that we were successful in providing a Python front end for the Tupleware package. It seems like it wouldn't be so much more painful to write it in Python than it would be in C++. There is, however, a ton of work to be done, and since I don't actively work on this anymore, as I mentioned, I work for MongoDB, where I do a bunch of other systems programming, but this is on the back burner for now. If anybody is interested in contributing, I would love to see some other people work on this. But that's it. So I want to thank a bunch of people. Tim Kraska was my advisor on this project. Alex, Andrew, and Kaihan are the PhD students who actually work on Tupleware. Thank you to the people who wrote Py2LLVM. I sincerely hope you don't mind that I've been mucking about in your code. Also to Jesse and Bernie, who are my two mentors at MongoDB, for encouraging me to give my very first PyCon talk. And of course, thank you to PyCon for having me.
Very much.
So, hold on.
Thank you very much.
In the interest of saving my voice, I'm going to go drink a vat of tea and then take questions. If anybody wants to tweet at me, email me, come talk to me after at the conference and they have questions, I would love to take them. I'd love to talk about it if anybody feels like they have something to say.
Yeah, thank you, Anna. A general announcement. After lunch, all the sessions are running a little bit late, so the next session is starting at 3:20. Just to get all sessions in sync again. And yes, as mentioned, Anna, you don't want any questions, do you? Yes, Anna's happy to take questions after. So yeah, thanks again, Anna.